April should feel like a warning bell, not summer at full force, yet across more of the world. Dangerous heat is arriving earlier, settling harder, and staying longer than the season once allowed. This is not just a hot week. It is a climate signal written into the calendar itself. In this video, April heat wave warning. The climate signal we can't ignore. The story follows how sunlight, atmosphere, dry land, cities, and the human body turn early season heat into a growing global danger. Before we begin, please like, subscribe, and join the channel for more calm, science-based documentaries that make complex climate stories clear. The planet turns through April beneath a changing angle of sunlight, and the broad face of Earth receives energy in a pattern that is never still, never perfectly balanced, and never the same from one latitude to another. At this time of year, the sun stands higher each day over the northern hemisphere, while the southern hemisphere moves gradually away from its warmer season. The difference begins not at the ground but in space, where sunlight arrives as a steady flow of energy and meets a tilted world. Earth's axis remains inclined as the planet circles the sun, and because of that tilt, the line of greatest solar intensity drifts northward through the year. In April, that line has already left the equatorial region and continues its seasonal movement, changing the length of day, the height of the midday sun, and the amount of energy that can be absorbed at the surface. From far above, the planet appears calm. White clouds spiral over oceans. Long continents stretch through different climate zones, and the blue atmosphere forms a thin veil around the globe. Yet the calm appearance hides a restless distribution of heat. Sunlight does not warm all parts of Earth equally, because the surface is curved. Near the equator, incoming light strikes more directly and concentrates its energy over a smaller area. Farther poleward, the same sunlight arrives at a slant and spreads across a wider surface. April sharpens this contrast in a special way. In the northern hemisphere, many regions now receive a rapid increase in daily solar input, not because the sun suddenly grows stronger, but because daylight lasts longer and the sun climbs higher in the sky. The change can feel gentle from one day to the next, yet over several weeks it becomes substantial. The oceans respond with patience. Water warms slowly because it can store large amounts of heat and mix that heat through depth. Land responds more quickly. Soil, rock, dry grass, roads, and roofs can rise in temperature much faster under clear skies. From the planetary view, this difference between land and sea becomes one of the most important features of April. Continents in the northern hemisphere begin to heat decisively, while nearby oceans often remain cooler, still carrying some of the thermal memory of the previous season. This growing contrast influences the atmosphere above them. It shapes pressure patterns, wind flows, and moisture transport, though at the global scale it first appears as an uneven quilt of warming surfaces. Some places absorb and re-radiate heat readily, others hold back, moderated by water, cloud, elevation, or lingering snow. April also lies in a seasonal interval that can create strong sensitivity. In many subtropical and temperate regions, the cool season has already weakened, but the full moisture and cloud patterns of later warm months have not yet become established. The result is often a period when the sun can work with unusual efficiency at the surface. Days lengthen. Skies may remain relatively clear. Vegetation in some regions has not yet reached its fullest growth. Snow cover, where it existed, may retreat and expose darker ground beneath, allowing more solar energy to be absorbed. This process changes the reflectivity of the surface. Reflectivity is the fraction of sunlight that a surface sends back into space. Bright snow reflects much of it. Dark soil, forest, and city material absorb more. As bright surfaces shrink and darker ones expand, the planet's seasonal heating can accelerate locally. From this outer view, a heat wave does not begin as a single hot afternoon. It begins as part of a broader energy story. The climate system is always moving energy from where it is abundant to where it is scarce. The tropics receive more solar input than the poles, and atmosphere and ocean work constantly to reduce that imbalance. Winds carry warm air poleward. Ocean currents transport heat through vast basins. Water evaporates, moves as vapor, and later releases heat when it condenses into cloud and rain. Even so, the balance is never smooth. Temporary build-ups occur. Regions can store excess warmth for days or weeks when the usual pathways of redistribution weaken or stall. A heat wave is one expression of that temporary concentration. Seen from the scale of the whole planet, it is a local intensification inside a larger and continuous exchange. April is especially revealing because it sits early in the warm season for many heavily populated parts of the Northern Hemisphere. When unusual heat appears at this stage, it often signals that the background conditions are already favourable for rapid warming. The atmosphere does not need to invent entirely new physics. It only needs the ordinary spring increase in solar energy to combine with certain surface and circulation patterns. In that sense, early season heat can act like a marker. It draws attention not merely because temperatures rise, but because they rise at a moment when many natural and human systems are not yet adjusted to sustained warmth. The global perspective makes this clear. The same planetary geometry that produces spring also opens a window in which modest shifts in clouds, wind, soil moisture, or air pressure can have large effects on surface temperature. Long-term climate warming adds another layer to this global picture. The planet now holds more heat than it did in earlier decades because greenhouse gases reduce the rate at which Earth loses thermal energy to space. This does not make every April heat wave identical, and it does not mean each event has a single cause. Observations indicate that global average temperature has risen markedly since the late 19th century, and that many regions experience more frequent and more intense heat extremes as a result. It remains uncertain in some individual cases exactly how much a specific event is amplified by climate change compared with natural variability, but the broader signal is clear. A warmer baseline raises the floor beneath weather. When favourable weather patterns develop, they now operate in an atmosphere and at a surface that are often already warmer than in the past. From orbit, none of this appears dramatic in a cinematic sense. There is no visible line that says a heat wave has begun. There's only a world receiving sunlight, storing part of it, reflecting part of it, moving part of it through air and water, and slowly shifting the seasonal balance northward. Yet within that ordinary motion lies the foundation of unusual heat. April brings longer days across vast land areas. The sun climbs, surfaces respond, and the contrast between land and sea grows sharper. The atmosphere above this uneven warming begins to organize itself around the difference. What later becomes a warning at the ground first exists here as a planetary arrangement of light, surface, and stored energy. The outermost region of this story remains simple in form and profound in consequence. Earth is a tilted sphere under spring sunlight. Land and water do not warm at the same pace. Bright and dark surfaces do not reflect the same amount of energy. A warmer climate alters the background state on which ordinary seasonal changes unfold. These are not rare mechanisms. They are the normal structure of the planet in April. But when they align in certain ways, ordinary seasonal heating becomes exceptional surface warmth. At the widest scale, the warning begins not in one city or one afternoon, but in the annual return of stronger sunlight to a hemisphere, falling upon a planet whose energy balance is already under strain. Across the planet in April, the broad belts of warmth and pressure continue their seasonal migration, and the movement is slow enough to seem almost fixed, yet powerful enough to shape weather across continents and seas. The sun's most direct rays now favour latitudes north of the equator, and the atmosphere responds by adjusting the position of its major circulation zones. These are not hard lines in the sky. They are wide regions where rising air, sinking air, clouds, dryness, winds, and storms tend to gather in repeating patterns. As spring advances in the northern hemisphere, these bands shift with it, carrying the possibility of early intense warmth into places where the ground is becoming newly receptive to heat. Near the equatorial zone, strong solar heating still drives deep convection, the upward motion of warm, moist air that forms large cloud systems and frequent rainfall. This region of rising air follows the annual march of maximum sunlight, though it does not move in perfect step with the sun. Oceans, land surfaces, and mountain ranges all affect its exact position. Even so, April often brings a gradual northward lean in this tropical belt, and that shift matters far beyond the tropics themselves. It changes where moisture gathers, where clouds are more likely to form, and where large-scale pressure differences begin to strengthen. The atmosphere is a connected system. When rising motion becomes more active in one broad zone, sinking motion tends to strengthen elsewhere. Heat waves often develop under the influence of sinking air, so this great seasonal rearrangement becomes part of the early framework. Poleward of the main tropical rain belt lie the subtropical regions, where descending air is common. Descending air is air that moves downward through the atmosphere, compresses, and warms as pressure increases. This process discourages cloud formation and often supports dry, bright conditions at the surface. In April, the subtropical high-pressure belts can begin extending their influence farther over land in the northern hemisphere. Their exact shape changes from day to day, but the broader pattern is familiar. Regions under or near these zones may experience clearer skies, weaker weather disturbances, and increasing solar heating at the ground. This is not yet a local heat wave by itself. It is the migration of a favourable belt, a seasonal broadening of the atmospheric space in which heat can build more easily. The contrast between land and ocean sharpens the effect. As continents warm faster than surrounding waters, pressure patterns adjust in response. Warm land tends to encourage rising air near the surface, while cooler oceans can maintain relatively denser air nearby. This growing difference helps organize regional flows and supports the reorientation of weather systems. In some places, it strengthens the draw of air from sea toward land. In others, it allows subtropical influence to press inland before moist seasonal circulation fully develops. April often stands in this intermediate state. The global circulation is shifting, but not all regional monsoon systems or summer rain patterns have matured. That gap can leave broad land areas exposed to intense sunlight with limited cloud cover and inconsistent moisture supply. The moving bands of warmth do not act alone. They meet surfaces that are warming rapidly and are not yet fully buffered by later seasonal rain. Farther poleward, the middle latitudes remain active with travelling weather systems, but even here the seasonal redistribution of warmth begins to alter their paths and their effects. The boundary between colder polar air and warmer subtropical air, often called the polar front, still guides many storms. In April it remains important, yet the whole thermal structure of the hemisphere is changing. The northward expansion of warmer air masses can reduce the frequency of cold intrusions into some regions, or shorten their duration, allowing warmth to persist longer between frontal passages. The result is not a simple, steady warming. It is a shift in odds. A warm spell that might once have been interrupted quickly can now last longer if the large-scale belts have moved into a more favourable position. This seasonal movement also changes the timing of heat exposure. When the warm belts arrive earlier or more forcefully than average, areas that normally expect mild spring conditions can be drawn suddenly into much hotter air. The importance of this lies not only in the temperature itself, but in the speed of transition. Early season heat often follows a period when nights are still expected to cool effectively, and when vegetation, soils, water systems, infrastructure, and human routines are tuned to a gentler season. The broad atmospheric bands do not know anything of calendars, yet their position in April helps determine whether a region experiences an ordinary spring warm spell or an event that reaches into dangerous territory. At the planetary scale, these belts are also influenced by the distribution of sea surface temperatures. Warm ocean regions can add heat and moisture to the lower atmosphere, while cooler waters suppress evaporation and moderate nearby air. In April, differences among ocean basins matter. Some regions of ocean warmth can encourage stronger moisture transport or alter the preferred tracks of large atmospheric features. Natural variability, including year-to-year changes in tropical ocean temperatures, can shift circulation patterns and influence where warmth pools over land. Observations indicate that such variability can enhance or suppress regional heat in any given season. It remains uncertain in some cases exactly how much influence comes from a particular ocean pattern during a single event, but the general relationship is well established. The migrating belts of heat and pressure do not float in isolation. They respond to the temperature pattern of the oceans beneath them. Long-term warming adds weight to this migration. As the climate warms, the warm side of many seasonal boundaries becomes warmer still. The subtropical air moving poleward in spring often carries more heat than similar air masses did in the past. At the same time, some studies suggest shifts in circulation characteristics in certain regions, though the details remain an active area of research and can vary by season and location. What is firmly observed is that the baseline from which these April patterns operate has risen. When the bands of warmth move north, they do so in a climate system already holding more energy. This does not erase natural seasonal movement. It intensifies its consequences. The atmospheric belts continue to migrate as they always have, but the temperatures associated with them can now be higher. Seen from the outer scale of the planet, the April heat warning is still not a local story of streets, homes, or bodies. It remains a story of moving zones. The tropical belt of rising air leans northward. The subtropical regions of sinking air and frequent sunshine expand or shift in influence. The middle latitudes adjust to a changing contrast between warm and cold air masses. Land warms faster than sea, sharpening gradients and reorganizing circulation. Ocean temperatures nudge the pattern further. The whole structure remains broad, slow, and atmospheric. Yet within this migration lies the first recognizable climate signal of unusual heat. The world is not merely warming in place. Its seasonal zones are also carrying that warmth into new spring positions, sometimes sooner, sometimes more strongly, and often over land surfaces ready to amplify the result. In this region of the story, the warning is written as motion rather than impact. It appears in the seasonal advance of warm belts, in the poleward reach of air that favours clear skies, and in the widening space where spring can turn quickly into dangerous heat. Nothing here depends on a single cloudless day or a single local forecast. The process is larger and quieter. It is the atmosphere adjusting to the sun's northward season. redistributing warmth through broad bands that slide over the globe with patient force. As these belts settle into their April positions, they define the areas where heat can begin to accumulate with unusual ease, and they prepare the stage on which more persistent atmospheric structures may soon hold that warmth in place. Above the weather that people feel at the ground, the higher atmosphere carries slow rivers of air that help shape the limits of warmth below. In April, these upper layers remain in transition, still influenced by the fading temperature contrasts of the cool season, yet increasingly adjusted to the growing warmth of spring in the northern hemisphere. The change is not visible in ordinary daily life. It unfolds far overhead, in broad currents and gentle undulations that guide where storm systems travel, where air descends, and where stillness can settle over large regions. A heat wave at the surface often appears to begin with hot afternoons and weak relief at night, but one of its early structures can already be found in these higher flows, where the atmosphere organizes motion on scales much larger than any city or valley. One of the most important features in this region is the jet stream. The jet stream is a narrow band of strong winds high in the atmosphere, usually found where cold and warm air masses meet most sharply. It does not move in a straight line around the globe. It bends, sways, and forms large waves as it circles the hemisphere. In colder months, when the contrast between polar and lower latitude air is strong, the jet stream often becomes more vigorous. In April, that contrast weakens gradually, but it does not disappear. The jet stream remains active, and its waviness can become especially important where it dips southward. Cooler unsettled conditions may be favoured. Where it arches northward, warmer air can spread poleward and remain in place longer than usual. These northward bulges, when they persist, can become part of the atmospheric architecture that supports early intense heat. The upper atmosphere does more than carry wind. It also helps determine whether air below rises or sinks. Rising air tends to encourage clouds, storms, and the release of stored heat through weather. Sinking air does the opposite. It compresses as it moves downward and warms in the process, often suppressing cloud formation and reducing the chance for widespread rain. In April, when the ground is already receiving stronger sunlight and many land areas are warming quickly, this downward motion can become especially effective if the upper level pattern favours subsidence, which is the slow sinking of air through the atmosphere. Then surface heat can deepen day after day under clear skies. The result is not merely more sunshine, it is a broader atmospheric lid that limits vertical mixing and helps the lower air mass remain stable and warm. These upper level patterns often develop as large ridges and troughs. A ridge is an elongated zone of relatively high pressure aloft and warmer air in the middle and upper atmosphere. A trough is the opposite, an elongated zone of lower pressure aloft, often associated with cooler air and more unsettled conditions. In April, ridges can build over continents that are already warming faster than nearby oceans. Once established, they may bend the jet stream around them and reduce the speed at which weather systems pass through. This slowdown matters. A brief ridge may produce a pleasant warm spell. A stronger and more persistent ridge can allow heat to accumulate over a region until the event becomes dangerous. The atmosphere above then acts not as an active remover of heat, but as a guardian of stillness, keeping the same general pattern in place. The height of the air column is also important. Warm air expands, so meteorologists often observe that ridges correspond to higher geopotential heights, which are measurements used to describe how high a given pressure surface sits in the atmosphere. In plain terms, a warm and thick air column occupies more vertical space. During periods of building heat, these heights can rise over a region, reflecting the growing warmth through a deep layer of air. This is one reason upper-level observations are so useful in understanding heat events. They reveal that the warmth is not confined to the ground. It often extends well upward, creating a vertically coherent structure that is harder to disrupt. Once such a pattern becomes established in April, when seasonal sunlight is strengthening rapidly, the surface beneath it can warm with notable efficiency. The high atmosphere also influences how much fresh air enters a region. Strong, progressive upper winds can move weather systems along and sweep away heat before it settles for long. But when the flow becomes weaker or more contorted, warm regions can remain trapped under the same broad pattern. A ridge can steer disturbances around its edges, leaving the centre relatively untouched. This does not require complete stillness. There may be local breezes, mountain winds, or sea influences below. Yet the large-scale framework remains unchanged. Hot air is not effectively replaced. Clouds do not arrive in lasting numbers. Surface heating continues under an upper pattern that quietly favours endurance rather than change. In April, the upper atmosphere may carry another subtle signal. The seasonal shift from winter towards summer often reduces the frequency of strong cold intrusions into some subtropical and temperate regions. This does not mean cold air vanishes. It means the pathways that once delivered repeated cooling can become less dominant. Under those conditions, a ridge that forms in the right place may encounter less resistance from northward or poleward movement of storm tracks. Warmth can then expand into regions where it would not easily have settled a few weeks earlier. The timing is important. The ground is increasingly ready to absorb heat, but the atmosphere still retains some of the large-scale dynamical structures of the cooler season. This combination can produce episodes of amplified waviness, where a persistent upper ridge acts as a warm anchor over land. Climate change may influence some aspects of these upper-level behaviours, but the details remain an area of active research. Scientists continue to study whether warming in the Arctic, changes in land-sea thermal contrast, and shifts in large-scale atmospheric energy gradients affect the waviness, persistence, or position of jet stream patterns in consistent ways. Results differ among regions and seasons, and uncertainty remains over how strong these links are in individual cases. Even so, observations clearly show that when persistent ridges do form in a warmer world, the surface temperatures beneath them can reach higher values than similar patterns once produced. The underlying weather mechanism may be familiar, but the thermal outcome can be amplified by the warmer baseline climate. This makes the upper atmosphere an important part of the warning. It is not only the source of the local weather features but also the keeper of duration. Many dangerous heat events are defined not simply by how hot a single afternoon becomes, but by how long the pattern lasts and how little relief appears between days. The high-level ridge, the diverted jet stream, the steady sinking motion, and the restrained passage of storms all help create that persistence in April. This persistence can be especially striking because it arrives before many landscapes and communities have adjusted to regular summer heat. The upper atmosphere does not create the sun, the land, or the warming climate, but it determines whether those ingredients are allowed to work together without interruption. At this altitude, the story remains broad and patient. Air currents arch around the hemisphere, waves grow and lean, pressure surfaces rise in warm regions, sinking motion suppresses cloud formation, disturbances curve away from a stable ridge and fail to deliver meaningful cooling. The signal of heat is not yet a street-level experience, but the structure that permits that experience has already taken shape overhead. In April, the high atmosphere can become a quiet organizer of surface danger, not through violence or sudden change, but through steadiness. It arranges the sky so that warmth can remain, sunlight can continue its work, and the lower world can drift deeper into heat under a ceiling of atmospheric persistence. Over the warming continents of April, the broad patterns high in the atmosphere can settle into a more fixed arrangement, and when they do, the air above a region begins to resist change. This is the realm of blocking, a condition in which the usual procession of weather systems slows, bends, or stalls for an extended period. A blocking pattern does not appear at the ground as an object that can be pointed to. It is an atmospheric posture, a way the larger flow becomes arranged so that one region remains under similar conditions day after day. In the context of heat, this persistence matters as much as temperature itself. A single warm day can pass without great consequence. A blocked pattern can allow warmth to deepen, surfaces to dry, nights to remain warm, and the whole lower atmosphere to settle into a more dangerous state. A block often forms when a strong ridge of high pressure becomes unusually stable and difficult for neighbouring weather systems to dislodge. The jet stream, instead of moving steadily from west to east in a relatively smooth band, begins to loop around the ridge and send disturbances elsewhere. Storm tracks may be diverted poleward or equatorward, leaving the blocked area beneath long intervals of clear or nearly clear skies. In April, this can be especially effective over land because the seasonal increase in solar energy is already strong. Each day under the block begins with a surface that has not fully cooled, then receives another long span of sunlight. Warmth accumulates not only because heating is present, but because interruption is absent. The air within a blocking high tends to sink slowly. This descent is gentle, broad, and persistent. As the air sinks, it compresses and warms, which reduces relative humidity and discourages cloud growth. Relative humidity is the amount of water vapor in the air compared with the maximum the air could hold at that temperature. When air warms through compression, its capacity to hold moisture increases, so cloud formation becomes less likely unless new moisture is added. The sky often clears. The ground receives more direct sunlight. At the same time, the stable structure of the atmosphere reduces vertical exchange. Air near the surface can become trapped beneath warmer air aloft, a configuration that suppresses mixing. Under these conditions, the lower atmosphere becomes an efficient place for heat to remain. The persistence of a block changes the rhythm of a region. Normally, spring weather in many middle latitudes moves in pulses. A warm day is followed by clouds, wind, or rain. A cold front passes. A brief cool interval resets the surface. Then warmth returns again. Blocking interrupts that rhythm. The expected alternation weakens, and a new pattern takes hold in which the same type of weather repeats. Under a warm block, mornings begin mild, afternoons rise quickly, and evenings bring less relief than before. Even if daytime temperatures remain only moderately above average at first, the continuation of that anomaly allows the landscape to store increasing amounts of heat. Buildings, roads, dry soils, and lower layers of air all begin to shift upward together. By the time the most extreme temperatures arrive, the event has often already been maturing for several days. In April, the timing of a block can be crucial. The season is early enough that many places still expect cool nights and occasional refreshing weather systems. Vegetation may still be developing. Soil moisture may already be limited after a dry winter or early spring. Snow cover, if recently melted, may have withdrawn unevenly, exposing dark ground in one region while another remains cooler. Into this transitional landscape, a block introduces atmospheric stillness. It does not create the land conditions, but it allows them to express themselves more strongly. Dry ground becomes drier, bare surfaces absorb and re-radiate more energy. Air masses age in place rather than being replaced. The whole land atmosphere system begins to reinforce itself. A blocking pattern can also enlarge the scale of a heat event. Because it spans such a broad region, it often covers multiple countries or whole sectors of a continent at once. This means the air arriving from neighbouring areas may already be warm. Cooling breezes from outside the event become less effective because the surrounding environment offers little contrast. In some cases, the block establishes a clockwise circulation in the northern hemisphere around the high-pressure centre, drawing warm air from lower latitudes into its western and northern flanks while keeping the central region dry and sunlit. The exact path depends on the position of the high, but the result can be a wide dome of warmth extending through a deep layer of the atmosphere. The ground beneath such a pattern does not merely heat under local sunshine. It sits within a large reservoir of warm air. This kind of persistence also affects rainfall. When storms are steered away, clouds become less frequent and soil receives no replenishing moisture. Evaporation then begins to change. When water is available in soil or vegetation, part of the sun's energy goes into converting liquid water into vapor, which cools the surface. When moisture runs short, more of that same solar energy goes directly into raising temperature. Under a block, this change can happen rapidly. A few dry days can alter the surface energy balance enough to make the following days hotter still. The blocked atmosphere and the drying land thus form a feedback. The sky remains clear because the air is sinking and stable. The ground becomes hotter because moisture is limited. The hotter ground then warms the lower air further, strengthening the heat already held in place by the block. Scientists observe blocking as a recurring feature of atmospheric circulation, not as a rare anomaly beyond normal weather dynamics. What makes it important in the modern climate is not the existence of the mechanism itself, but the temperatures it can now support. A blocking high that might once have produced a strong warm spell can today produce more extreme heat because the background climate is warmer. Observations indicate that many recent heat events occur under persistent high-pressure systems of this kind. It remains uncertain how climate change may be altering the frequency, duration, or regional behavior of blocking in all parts of the world, and research continues on that question. But there is strong agreement that when a block forms over a warmer land surface in a warmer global climate, the resulting heat can become more intense. At the scale of human experience, a blocking pattern is often felt as repetition. The sky remains bright. The forecast changes little. The air grows heavier with stored warmth even when humidity is not especially high. In urban areas, nights begin to lose their cooling power. In rural areas, fields dry and winds weaken under stable conditions. Yet all of this begins in the broad stillness overhead. The block is not dramatic in motion. Its defining trait is the lack of motion. The way it holds a region under one atmospheric regime and keeps the ordinary mechanisms of change at a distance. This region of the story stays with that stillness. Over the continent, the high-pressure system settles and resists removal. Storms curve around it. Air sinks, warms, and suppresses cloud formation. Day follows day with little interruption, and the surface responds by storing more heat than it can release. In April, when the seasonal rise of sunlight is already strong and the landscape may be dry or exposed, this persistence becomes a powerful climate signal. The warning is no longer only in the general migration of warm zones or the shape of high-altitude flow. It is now in the refusal of the atmosphere to move on. Heat builds because the sky above the land remains locked in place, and the continent below is left to warm beneath a lid of steady, silent pressure. Beneath the blocking sky and below the higher patterns that guide it, The lower atmosphere gathers into distinct bodies of air that carry their own temperature and moisture traits across large regions. These are air masses, broad volumes of air that take on the character of the surfaces over which they form and travel. Near the ground in April, their influence becomes immediate. The season is no longer defined only by the angle of sunlight or the shape of distant circulation. It is now felt in the very substance of the air resting over fields, cities, plains, and valleys. A heat wave at this level is not an abstraction of global balance or upper air pattern. It becomes a lived condition shaped by what kind of air settles near the surface, how long it remains, and whether it arrives dry, humid, still, or slowly moving. An air mass that forms over warm, dry land tends to be hot and low in moisture. One that comes from cooler ocean water is often milder and may carry more humidity. In April, many regions lie at the meeting place of these possibilities. The land is warming quickly, but nearby seas may still be relatively cool. The subtropics may be supplying warm air from lower latitudes, while occasional spring disturbances still bring fresher air from other directions. Under ordinary conditions, these competing influences alternate and prevent any one character from dominating for long. Under a persistent high-pressure regime, that balance changes. One air mass may settle over a region and remain there long enough for its properties to deepen. It does not simply preserve the warmth it brought with it. It can become warmer still as sunlight acts on the surface beneath it. The lower atmosphere is where this daily exchange becomes intimate. During the day, sunlight warms the ground, and the ground warms the air directly above it. This near-surface layer responds quickly. If the air mass is already warm when it arrives, then the added heating can push temperatures sharply upward. If the air is dry, the temperature may rise especially fast because dry air often allows strong solar heating at the surface and can support large day-to-night swings. Though that nighttime cooling weakens when the whole lower atmosphere becomes deeply warmed. If the air is humid, the heat can feel heavier and more oppressive because water vapor reduces the body's ability to cool by evaporation. In both cases, the air mass shapes the character of the event. The same temperature can carry a different physiological burden depending on the moisture it contains. In April, this lower air structure often reflects the unfinished transition between seasons. Warm air from lower latitudes may advance into areas that recently experienced cool nights and mild afternoons, because the seasonal shift is still underway. This warmth can feel abrupt. The lower atmosphere is not yet routinely flushed by strong summer convection or organized rainfall in some regions. Instead, a warm air mass may arrive beneath clear skies and meet a land surface that is increasingly ready to heat, but not yet buffered by consistent moisture recycling. Over several days, the air mass becomes aged in place. This means it lingers over the same region and is modified by the surface below. Warmth increases from beneath. Moisture may diminish if soil dries and evaporation weakens. The air then loses some of its earlier marine moderation or transitional softness and becomes more continental in character, hotter and often harsher. The depth of the lower warm layer matters greatly. If warmth is confined to a very shallow layer near the ground, a modest breeze or overnight cooling may weaken it, but during a developing heat event, the warm air often thickens through a deeper portion of the lower atmosphere. Daytime mixing helps with this. Mixing is the process by which warmed air rises a little and exchanges with air above it, distributing heat vertically through the boundary layer, which is the part of the atmosphere most directly affected by the ground. In a stable high-pressure setting, daytime heating can still create a deep mixed layer, especially over dry land. Once this lower part of the atmosphere becomes broadly warm, it acts as a reservoir. The next morning begins not from a cool reset, but from a warm starting point. Each day then adds heat onto heat. The source of the air mass also determines how much relief comes at night. Dry continental air under clear skies can sometimes cool efficiently after sunset, especially early in an event. Yet when a heat wave matures, the accumulated warmth in soils, roads, buildings, and the air itself can reduce that benefit. Humid air behaves differently. Water vapor absorbs and re-emits heat, helping keep nights warmer in coastal or tropical regions. A humid air mass can therefore create particularly stressful conditions, even when daytime temperatures are not as extreme as in dry inland heat. April heat waves vary in this way across the world. Some are fierce and desiccating, marked by glaring light and very low humidity. Others are heavy and stifling, with warm nights that leave little recovery. The lower atmosphere carries these differences in its composition. Near the surface, winds also influence whether an air mass changes quickly or remains intact. Gentle transport from a cooler sea may temper the heat in one area, while failing to reach another farther inland. A warm downslope flow from elevated terrain may locally intensify temperatures by compressional warming, though such effects depend strongly on topography and regional setup. In flat continental interiors, warm air can spread widely and remain pooled over immense areas. The key feature in April is often not violent movement but insufficient replacement. The air mass over a region simply remains too similar from one day to the next. It stays warm, often becomes drier, and continues receiving heat from below under strong spring sunlight. This is also where climate change becomes easier to feel, even if it remains difficult to isolate in a single moment. A warm air mass arriving today is frequently warmer than a comparable air mass of the past, because the surfaces and oceans that help form it are warmer on average. Observations indicate that background warming has raised the temperatures of many source regions, meaning that when air moves poleward or inland, it often begins from a higher thermal baseline. It remains uncertain how much any specific April event depends on the exact origin of one air mass compared with local surface amplification, but the broader tendency is clear. The air settling near the ground now often carries more heat into spring than similar seasonal flows once did. At this level, the warning becomes personal in a new way, though the story still stays with the air itself. The lower atmosphere rests over towns and cropland like a shallow sea of warmth. It presses into streets in the afternoon and lingers in bedrooms after dark. It enters through open windows, moves across dry soil, and settles over reservoirs and rail lines. Yet all of this begins with the physical traits of the air mass. Is it dry or humid? Is it maritime or continental? Is it newly arrived or aged in place? Does it cool at night or hold its warmth until dawn? These are the near-surface questions that determine whether April heat is merely unusual or becomes physically dangerous. In this region of the topic, the heat wave is no longer simply a pattern of pressure overhead. It becomes a settled body of air near the surface, modified by the land beneath it and preserved by the stillness above it. Warm air remains over warming ground. Moisture conditions shape how the heat is felt and how easily nights can cool. Daytime mixing deepens the warm layer, and each morning begins from a higher starting point than the last. The lower atmosphere thus turns a broad atmospheric setup into something immediate and persistent. It is here, close to the ground, that the event begins to acquire texture, weight, and endurance as the same warm air remains in place and gradually becomes the atmosphere of the heat wave itself. Within the warm air settled near the surface, the movement of wind becomes one of the quiet forces that decides whether heat will deepen or disperse. Wind is often imagined only as motion felt on the skin, but in the lower atmosphere it performs a larger task. It transports air from one region to another, stirs layers together, carries moisture, and helps remove stored warmth from the ground. In April, when continents are heating quickly under stronger sunlight, the absence of effective wind can matter as much as the presence of strong sunshine. A heat wave grows not only because energy arrives, but because too little of that energy is carried away. The lower atmosphere becomes a place of weak renewal, where air lingers over the same surface and takes on more of its heat with each passing day. Under a persistent high-pressure pattern, surface winds are often reduced or loosely organized. The broad sinking of air discourages the growth of strong storm systems nearby, and the pressure differences that drive active horizontal flow may remain small over the hottest region. Some local breezes still form. Air may drift upslope by day along hillsides, settle downslope at night in mountain areas, or move short distances between land and water near coasts. But these are often limited in reach. They do not always penetrate far inland, and they may not be strong enough to replace the aging air mass that has already become warm. The result is a kind of atmospheric residence. The same near-surface air remains over a region long enough to be heated repeatedly by the land below. This weak movement changes the daily cycle of temperature. During the day, sunlight warms exposed surfaces, and those surfaces warm the air directly above them, if wind remains light. The newly heated air is not quickly swept away. It accumulates close to the ground and contributes to the growth of the daytime boundary layer. A stronger wind might mix in somewhat cooler air from elsewhere, or transport the warmed air away before it intensifies too much over one location. Under light wind, the exchange is slower and less effective. The ground and the air above it remain coupled. A hot surface produces hot air, and that hot air remains nearby long enough to amplify the next stage of heating. In dry inland regions, weak winds can make the afternoon atmosphere feel still and heavy, even when humidity is low. There may be brief gusts produced by local turbulence, but little sustained ventilation. Over moist regions, the effect can be even more burdensome because the limited air movement reduces the body's ability to cool by sweat evaporation. A breeze can help remove the thin, humid layer of air that forms near the skin. When the wind slackens, that relief diminishes. This is one reason a heat wave with only moderate wind can feel more oppressive than one with stronger airflow at the same temperature. The surrounding air is not renewed quickly enough, and heat remains trapped not only in the landscape, but also in immediate human surroundings. The failure of wind to cool is especially important at night. In ordinary spring conditions, evening often brings more than darkness. It brings a change in air movement. Cooler air can drift into valleys, marine air can move inland, or larger-scale winds can shift enough to disturb the day's warm layer. During an April heat event under stable high pressure, those cooling mechanisms may weaken. The land releases some of its stored heat after sunset, but the overlying air remains warm and is not effectively replaced. If winds stay light, especially in cities or enclosed inland basins, the heat released by buildings, pavement, and dry ground stays concentrated near the surface. Warm nights then become one of the clearest signs that the event is maturing into something more dangerous. Wind also influences moisture exchange between surface and atmosphere. Where soil still contains water, moving air can enhance evaporation by carrying away the moisture that rises from the ground and vegetation. But if the broader weather pattern has already reduced rainfall and the surface is drying, this process changes. Less water is available to evaporate, and a weak wind cannot compensate for that loss. Instead of sustaining evaporative cooling, The land increasingly channels incoming solar energy into sensible heat, which is the direct warming of air. When winds are light, that sensible heat remains concentrated in place. The surface and lower atmosphere thus enter a reinforcing loop. Drying limits cooling. Weak wind limits transport. Temperatures rise more easily because both release valves have narrowed. In coastal regions, the role of wind becomes more subtle. A sea breeze can moderate daytime heat near shore because cooler marine air moves inland as land warms faster than water. In April, however, that cooling influence often has clear limits. If the background high-pressure system is strong, or if the regional flow opposes inland penetration, the marine air may only reach a narrow strip near the coast. Farther inland, the heat persists, even near shore. The air may become humid rather than truly cool, reducing physiological relief. In some cases, weak synoptic flow allows a sea breeze to form but also allows it to stall or remain shallow. The presence of a breeze then gives only partial comfort, while the interior continues to warm intensely. What matters is not the existence of some air movement, but whether the movement is strong and deep enough to replace the warm boundary layer over a broad region. Topography adds another layer to this stillness. Valleys can trap warm air beneath stable conditions, especially where overnight drainage flows are weak or where surrounding slopes re-radiate heat after sunset. Plateaus and enclosed basins may develop strong daytime heating because the air over them is dry and mixing is deep. Yet the broader regional wind remains too weak to remove the warmth efficiently. In cities nestled inland, buildings disrupt airflow and create pockets of stagnation at street level. The heat wave then acquires local textures of stillness. One neighborhood may lie under a faint moving breeze while another, shielded by buildings or terrain, remains stifling and motionless. Scientists observe that heat extremes often coincide with stagnation, a term used for weather conditions with weak winds and limited ventilation near the surface. Stagnation can also worsen air quality because pollutants are not dispersed effectively. In April, this combination can be especially harmful. The season may encourage outdoor work, travel, and early agricultural activity. Yet the atmosphere offers little protection from heat buildup and may also concentrate harmful particles or ozone near the ground. Observations indicate that stagnant conditions frequently accompany persistent high-pressure events. It remains uncertain in specific regional cases how much long-term climate change will alter the frequency of stagnation itself, but the warming baseline clearly increases the thermal consequences when stagnant conditions occur. At this near-surface level, the warning becomes one of failed escape. Heat arrives from sunlight and from the warm air mass already in place, but it is the weak movement of air that allows the event to settle into endurance. Breezes that might have refreshed a region remain shallow, delayed, or absent. Winds that might have transported warmth away become too faint to matter. Daytime heating therefore accumulates close to the ground, and nighttime cooling becomes partial and unreliable. The atmosphere over the land no longer behaves like a flowing medium carrying conditions onward. It behaves more like a vessel holding them in place. In this region of the story, the heat wave is shaped by quietness. The air near the surface does not move enough to cleanse the day. Warmth remains over dry land, around buildings, above roads, and within valleys. Moisture is not transported effectively. Cooler air is not delivered reliably, and relief fails to arrive in full. The result is a heat that feels settled rather than passing, a climate signal expressed through weak motion. April sunlight continues its work, but the deeper warning lies in the lack of atmospheric removal. Heat remains because the wind, one of the ordinary agents of balance, has become too slight to restore it. Above the warmed land and within the weakened flow of surface air, the passage of sunlight through the sky becomes the next decisive layer of the event. In April, the difference between a day softened by cloud and a day left open to the sun can be large. When a heat wave develops, this contrast is repeated not once but over many days, and the repetition is what matters. The surface is exposed morning after morning to a long interval of radiant energy, and with little interruption from cloud. The energy is absorbed by soil, vegetation, buildings, roads, and the lower air above them. At this stage, the warning is written in light itself. The atmosphere is not only warm and still, it is also transparent enough to let the season's growing sunlight reach the ground with unusual efficiency. Clouds normally act as regulators of surface heating. They reflect part of the incoming sunlight back to space and reduce the amount that reaches the surface directly. Thick clouds can keep daytime temperatures markedly lower than they would otherwise be. Even in spring, when the sun stands high, thin clouds have a subtler effect, scattering some light while still allowing substantial energy through. During a heat wave, cloud cover is often reduced because the air aloft is sinking and drying. This suppresses the vertical development of large cloud fields and leaves wide skies clear for much of the day. The result is a sequence of afternoons in which solar radiation, meaning energy from the sun, arrives with little obstruction. The ground responds quickly, especially where soils are dry and surfaces are dark. In April, this process carries special force because the season is advancing rapidly. Day length is increasing across the northern hemisphere, so the total time available for solar heating grows longer, week by week. The midday sun is also climbing higher, which allows its rays to strike the surface more directly than they did earlier in the year. Even without any unusual atmospheric pattern, this seasonal change would raise temperatures. Under a persistent warm regime, the effect is magnified. The same clear sky that might once have produced a mild spring afternoon now produces strong heating, because both the sun and the background air mass have shifted to a warmer state. The heat wave thus feeds on ordinary astronomy and ordinary weather at the same time. Nothing about the sun is abnormal. What changes is how fully the atmosphere allows its energy to reach the land, and how effectively the land converts that energy into heat. The quality of sunlight matters as well. Direct sunlight, arriving without much cloud interference, heats exposed surfaces more intensely than diffuse light scattered through a cloudy sky. Asphalt, stone, dry soil, metal roofs, and building walls absorb a large share of that direct radiation and become much hotter than the air. These hot surfaces then transfer energy upward through conduction and convection. Conduction is the direct transfer of heat through contact. Convection is the transfer of heat by the motion of air. A patch of pavement in full sun may grow much hotter than the surrounding atmosphere and then warm the air just above it, helping lift the temperature of the lower boundary layer over a region with many exposed surfaces. This process operates on a wide scale. Clear skies allow not just more warmth, but more effective coupling between sunlight and the materials of the landscape. Cloud absence also influences how evenly heating is distributed through the day. In a partly cloudy pattern, intervals of sunshine alternate with shade, and surface temperatures can rise and pause in cycles. During persistent clear conditions, the heating becomes smoother and more cumulative. From morning onward, the ground keeps gaining energy with few interruptions. By early afternoon, the boundary layer deepens and warm air spreads through a greater thickness near the surface. By late afternoon, roads, walls, rooftops, and bare earth may continue radiating heat even as the sun begins to fall. the day acquires a long thermal tail. This repeated continuity of heating is one reason multi-day clear spells can be more dangerous than isolated bright days of similar intensity. In some regions, a heatwave may include high thin cloud that does little to stop the warming. Such cloud can slightly soften the light without preventing strong heating at the surface. In other cases, haze or suspended dust may alter the sky's appearance while still allowing enough solar radiation through to maintain dangerous warmth. The key factor is not whether the sky looks perfectly blue at every hour, but whether cloud cover is substantial enough to interrupt the daily gain of energy. During a strong April heat event, it often is not. The atmosphere remains dominated by conditions that favour exposure. Sunlight reaches the land early, persists through much of the day, and returns again the next morning to a surface that has only partly shed the previous day's stored heat. The role of nighttime cloud is different but also important. Clouds after sunset can trap outgoing heat and keep nights warmer by re-emitting some of the long-wave radiation leaving the surface. Under many hot, dry, high-pressure events, nights remain relatively clear, which can allow some cooling. Yet if the air mass is already warm, the surface is dry, and buildings and ground materials have stored large amounts of heat. That clear sky cooling may still be limited. In humid regions, or where some cloud lingers overnight, relief may be reduced even further. Thus clouds regulate both day and night, though in different ways. For daytime heat growth, the key danger often lies in their absence. For nighttime recovery, either their presence or the accumulated warmth of the surface can maintain stressful conditions. This layer of the story also reveals a basic scientific contrast between weather variability and climate signal. A few cloudless days in April can happen naturally in many regions and have always happened. But when such days occur in an atmosphere and on a surface that are warmer than in the past, their effect can become more severe. Observations indicate that global warming raises average temperatures and makes hot extremes more likely when cloud-free, high-pressure conditions occur. It remains uncertain in some regions whether long-term climate change will systematically alter cloud patterns in every season and place, because cloud behavior depends on many interacting processes. Even so, the role of clear skies in amplifying surface heat is well understood. When the clouds fail to gather, the sun's spring energy is expressed more fully at the ground, and a warmer baseline makes the outcome hotter. At the scale of daily experience, this part of a heat wave is often remembered as relentless brightness. Morning light arrives already carrying the promise of difficult afternoon heat. Shade becomes valuable because surfaces in direct sun warm so quickly. Indoor spaces exposed to sunlight take on heat through walls and windows. Agricultural land dries faster. Reservoir levels may fall gradually as evaporation continues under repeated bright days. Yet all of these consequences begin with the simple atmospheric fact of reduced cloud cover. The warning does not need thunder or dramatic winds. It can arrive through stillness and light, through a sky that remains too open for too long. In this region of the topic, the heat wave is shaped by exposure. The warm air mass remains in place. Winds fail to remove its heat, and now the sky allows strong April sunlight to reach the surface day after day. Cloud regulation weakens. Direct radiation strikes dark ground and built materials. The lower atmosphere warms from below, and the event deepens through repetition rather than surprise. The climate signal becomes clearer because ordinary spring sunshine, under unusually favourable atmospheric conditions and on a warmer planet, produces extraordinary surface heat. Here the warning rests in the brightness of repeated clear days, in the uninterrupted transfer of solar energy into land and air, and in the quiet efficiency with which the open sky turns seasonal warmth into sustained April heat. At the edge where land meets water, April heat begins to reveal a contrast that is both familiar and scientifically precise. Coasts and interiors do not warm in the same way, even when they lie under the same broad sky and within the same regional air mass. The difference begins with heat capacity, the ability of a material to store energy without changing temperature quickly. Water has a high heat capacity. Land generally does not. Because of this, the sea resists rapid warming in spring, holding much of the cool memory of earlier months, while nearby ground surfaces respond more quickly to the strengthening sun. The result is a boundary between moderation and acceleration. Along many coasts, the presence of the ocean slows the rise of air temperature. Farther inland, where the influence of water fades, the same April sunlight can produce much stronger heat. This contrast does not mean that all coasts remain cool, or that all inland regions become equally hot. Local geography, wind direction, ocean currents, humidity, and topography all shape the result. Yet the broad principle remains steady. The ocean changes temperature slowly because sunlight is mixed downward through moving water, because evaporation consumes energy at the surface, and because the water body itself stores large amounts of heat before warming noticeably. Over land, the incoming energy is often concentrated into a thinner, less mobile surface layer. Dry soil, rock, roads, and sparse vegetation can warm quickly by late morning. That warmth is then transferred to the air above, in April, when northern land areas are climbing toward the warm season but adjacent seas may still be relatively cool. This difference becomes especially pronounced. Near the coast, marine air often acts as a buffer. Air that has recently travelled over cool water may arrive at the shoreline milder than the air farther inland. Even under sunny skies, this can limit daytime temperature, especially where onshore flow is persistent. The coast then experiences a different version of the same weather pattern. The high-pressure system may be present, the skies may remain mostly clear, yet the ocean modifies the lower atmosphere enough to prevent the sharpest daytime heating. This moderation can be narrow. A coastal strip may feel bearable while inland districts only a short distance away warm rapidly into dangerous conditions. The transition may be gradual across an open plain or abrupt where terrain rises just beyond the shore. Sea breezes are one of the clearest expressions of this contrast. During the day, land warms faster than water, and the air above land rises more readily. Cooler, denser marine air then moves inland to replace it. This circulation can soften afternoon heat near the coast, sometimes by a large amount. In April, however, its reach is often limited. If the larger weather pattern is strongly dominated by high pressure and sinking air, or if regional winds oppose inland movement, the sea breeze may remain shallow or confined to a narrow zone. Farther inland, the surface continues heating with little marine relief. In some cases, the breeze arrives late, after substantial warming has already occurred, and only reduces the temperature briefly before evening. The coast then becomes not a cool refuge in an absolute sense, but simply a less extreme margin beside an overheated interior. Humidity complicates this coastal moderation. Marine air often contains more moisture than continental air, and while this can lower maximum daytime temperature, it may also make the heat feel heavier and reduce nighttime relief. A humid coastal area can remain stressful even when the inland maximum temperature is higher. The body cools through the evaporation of sweat, and moist air weakens that cooling by slowing evaporation. Thus, the ocean can moderate temperature while increasing discomfort. In April, this is especially important in warm subtropical and tropical regions, where nights near the coast may remain warm and damp. The heat wave there takes a different form. It may be less intense in pure temperature terms than inland heat, but more oppressive for human health because recovery is limited. Farther from the sea, inland regions lose this moderating influence. The air mass becomes more strongly shaped by the land beneath it. Over many days of clear weather, the ground warms rapidly, especially if soil moisture is low and vegetation is sparse or not yet fully developed. The boundary layer over inland plains and plateaus deepens through repeated daytime heating, and the absence of nearby cool water means there is little external reservoir to temper the process. Temperatures can then rise quickly from morning into afternoon and stay elevated from one day to the next. Inland heat in April often has this cumulative quality. It does not rely on a single burst of extreme weather. It grows because the surface keeps receiving energy and has few ways to discharge it. Distance from the sea also affects seasonal timing. Coastal waters often delay the onset of strong spring warmth, while continental interiors race ahead under clear skies. This is why April heat can become severe first in inland zones, even when coastal areas remain comparatively moderate. The ocean acts like a seasonal anchor, slowing transition. Inland land surfaces act more like amplifiers, responding quickly to each increase in solar input. When a persistent high-pressure event covers both regions, the result is a strong thermal gradient, a change in temperature over distance between shoreline and interior. That gradient can influence local winds, cloud development, and human vulnerability. Populations inland may face a much earlier and stronger onset of dangerous heat than those living closer to the sea. Large lakes can produce a similar but smaller effect. Though not equal to oceans in scale, they still warm and cool more slowly than surrounding land and can moderate adjacent areas in spring. Yet once one moves beyond their immediate reach, inland heating resumes its stronger pattern. Mountain ranges can further complicate the boundary. A coast backed by mountains may trap marine air near the shore, making the coastal plain mild while valleys beyond the barrier heat intensely. In other places, gaps in terrain allow sea influence to penetrate inland for some distance. The principle remains unchanged. Water resists rapid warming, land embraces it. April heat waves expose that contrast with unusual clarity. Climate change does not erase the coastal-inland difference, but it alters the baseline on both sides. Sea surface temperatures in many regions have risen over time, and land temperatures have risen even more quickly in many continental interiors. Observations indicate that land areas generally warm faster than oceans because of differences in heat capacity, evaporation, and atmospheric feedbacks. This means that the inland amplification of heat can become stronger relative to nearby waters, especially during clear, dry events. It remains uncertain in specific regional cases how changing ocean currents, marine cloud patterns, or coastal winds will modify the local detail of future April heat, but the broader signal is robust. The inland zones, already more prone to rapid warming, are often the places where early season heat becomes most intense. At the scale of lived experience, this contrast may appear as a quiet division within one region. Near the water, mornings begin cool or mild, afternoons warm gradually, and evenings may remain humid. Inland, the same sunrise leads to a much faster climb, with brighter glare from dry ground, hotter surfaces by midday, and greater storage of heat into the night. Farms, towns, transport routes, and power demand all reflect this difference. What appears on a map as a simple distance from the shore becomes, in thermal terms, a movement from restraint toward acceleration. In this region of the story, the April heat wave is shaped by proximity and separation. The sea holds back the season while the interior advances into it more quickly. Marine air softens some coasts but may arrive late, shallow, or heavy with humidity. Inland land surfaces, free from strong ocean moderation, absorb sunlight and raise air temperature with greater speed and persistence. The warning therefore takes on a geographical form. It is not evenly spread across the landscape. It grows stronger with distance from water, where the memory of the cool season fades fastest, and where April sunshine finds the least resistance. In that widening interior, the climate signal becomes clearer as spring warmth turns more readily into early dangerous heat. Away from the moderating edge of the sea and down at the level of the land itself, the heat wave enters one of its most decisive regions. The ground is no longer merely a receiver of sunlight. It becomes an active partner in the growth of extreme heat. In April, this partnership often turns on moisture, especially the moisture held in soil. Soil moisture is the water stored between particles of earth, available in varying amounts to evaporate into the air or to support plant life. When that water is abundant, part of the sun's energy is used to change liquid water into vapor. This process cools the surface because energy is spent on evaporation rather than on raising temperature directly. When the soil is dry, that cooling pathway weakens. The same sunlight then produces more sensible heat, meaning direct warming of the land and the air above it. A dry surface can therefore turn ordinary spring sunshine into unusually intense warmth. This shift in the surface energy balance is one of the clearest ways a heatwave strengthens itself. Early in spring, some landscapes still hold moisture from winter rain, melting snow, or recent storms. Under clear skies and mild temperatures, that moisture can moderate daytime heating. But if rainfall has been limited, or if several bright dry days have already passed under high pressure, the upper soil layers begin to lose water quickly. Evaporation continues until the surface dries enough that the rate falls. Then a threshold is crossed. The land can no longer spend as much solar energy on cooling through evaporation, so it begins spending more of that energy on heating itself. Temperatures rise faster, afternoon air grows hotter, and the lower atmosphere becomes more difficult to cool the following night. In April, this change can arrive quietly because the season often sits between wet and dry regimes. Some regions have not yet entered their rainiest period. Others may have emerged from winter with moisture already depleted by poor snowpack or dry seasonal conditions. Vegetation may still be developing, which means the landscape may not yet be returning large amounts of water to the air through full leaf growth. A heat event arriving during this interval finds the ground vulnerable. The days lengthen, the sun strengthens, and the block overhead suppresses rainfall. The land begins to lose water just as it is asked to absorb more solar energy than before. The heat wave then becomes partly a surface event. It no longer depends only on the air mass above. It is being fed upward by the drying earth. Dry soil changes temperature quickly because water is no longer present in sufficient quantity to buffer it. Moist soil warms more slowly, just as wet cloth warms more slowly than dry cloth left in the sun. In a dry field, bare ground can become extremely hot by afternoon, and this heat is passed to the air just above it through conduction and convection. The effect is strongest where vegetation cover is sparse or seasonal growth remains incomplete. Bare earth, harvested land, degraded grassland, and exposed construction zones often warm rapidly under clear skies. The heat wave then acquires a more local texture. One landscape may remain somewhat moderated by irrigated fields or shaded vegetation, while a neighbouring dry tract sends stronger heat into the boundary layer. Across a wide region, These differences add up and influence the total thermal burden of the event. The feedback between soil dryness and heat is powerful because it unfolds over several days. A hot day dries the surface further. The drier surface then becomes more efficient at producing even higher temperatures the next day. Rainfall that might have interrupted this process is diverted away by the persistent high-pressure pattern. Nighttime dew, where it forms at all, is too slight to compensate. Deeper soil layers may still contain some water. But if roots are shallow or vegetation is limited, that deeper moisture cannot fully protect the surface from daytime overheating. The upper ground becomes the critical interface. It is the thin layer that sunlight strikes first, and the layer from which much of the heat is transferred upward into the atmosphere that people experience directly. Soil texture and composition influence this process. Sandy soils tend to drain water quickly and may dry at the surface faster than heavier clay-rich soils, though clay can also harden and crack under prolonged drying, limiting water availability near the top layer. Organic matter helps soil retain moisture, so degraded or heavily disturbed land may lose its moderating capacity sooner. These details vary from place to place, but the general principle remains consistent across climates. When the land has less accessible water, it has less evaporative defense against strong solar heating. The atmosphere above that land then becomes hotter under the same amount of sunlight than it would if moisture were abundant. This drying also affects plants. Vegetation cools the air by transpiration, which is the release of water vapor from leaves. When soil moisture declines, plants may close tiny openings on their leaves to conserve water. This reduces transpiration and weakens another natural cooling process. The heat wave then intensifies further because both soil evaporation and plant transpiration are reduced. The land surface, stripped of these cooling mechanisms, channels more incoming energy into temperature rise. In April, this may happen before many ecosystems have fully entered their vigorous growing season, which can leave them less able to buffer an early hot spell. The result is a landscape that heats faster than expected for the time of year and gives back more warmth to the air. In agricultural regions, this matters deeply. Crops emerging into spring growth can face intense heat stress if an April event arrives while soil moisture is already low. Germination, flowering, and early development can be disrupted. Irrigation may soften the effect locally, but irrigation itself depends on water availability and infrastructure. In natural landscapes, dry leaf litter and grasses warm quickly, and the ground loses its cooling capacity. Reservoirs and streams may also reflect the same wider dryness, reducing the overall moisture supply available to the region. Thus, the soil moisture signal often extends beyond the field or forest floor. It becomes part of a larger land surface dryness that amplifies heat over entire districts. Climate change strengthens the importance of this region because warmer air increases evaporative demand. Evaporative demand is the atmosphere's capacity to draw water from the surface. When temperatures rise, the air can hold more water vapor, and under dry conditions it pulls more moisture from soil and plants. Observations indicate that many regions now face stronger drying during hot events, because the warmer atmosphere extracts water more aggressively. It remains uncertain how rainfall timing and soil moisture trends will evolve in every local area, but the physical link between heat and drying is well established. A warmer climate does not simply raise temperatures directly, it can also prime the land to lose moisture faster, which in turn makes later heat more severe. At this stage, the warning rests in the earth underfoot. The surface that once moderated sunlight by spending energy on evaporation begins to lose that ability. Bare ground heats quickly. Plants conserve water and reduce cooling. Each dry day makes the next hot day easier to produce. What appears from above as a spell of sunny weather becomes, at the level of the soil, a self-reinforcing exchange between dryness and temperature. April is especially sensitive because it can bring strong sunlight before reliable seasonal moisture returns, leaving the land exposed at precisely the wrong time. In this region of the story, the heatwave is no longer only in the air or sky, it is rooted in the ground. Soil moisture fades, evaporative cooling weakens, vegetation gives less water back to the atmosphere, and more of the sun's energy goes directly into heating land and air. The surface becomes an amplifier. Under repeated clear days and limited rainfall, dry earth turns spring warmth into something sharper and more persistent. The climate signal therefore deepens as the land itself begins to participate, not passively but actively, in the making of April heat. Within the broad heated landscape, the city forms its own thermal world. It does not stand apart from the April heatwave, but it reshapes that heat with materials, geometry, and stored energy. Streets, roofs, walls, parking areas, rail lines, and paved open spaces respond to sunlight differently from fields, forests, or moist ground. Many urban surfaces are dark, dense, and dry. They absorb a large share of incoming solar radiation during the day and release that energy slowly after sunset. This creates what scientists call the urban heat island, a pattern in which cities are often warmer than their rural surroundings, especially at night. In April, when a regional heat event settles over the land, the city can intensify its effects by storing more heat than nearby natural terrain, and by giving that heat back at the very hours when recovery is most needed. Concrete, asphalt, brick, stone, and roofing materials all have physical properties that make them important in this process. Many have low reflectivity, which means they absorb rather than reflect much of the sunlight that strikes them. Many also have substantial thermal mass, meaning they can store large amounts of heat within their structure. During a clear spring day, a city block may become much hotter than the air above it. Pavement in full sun can reach temperatures far beyond the official air temperature measured in shade. Building walls exposed to afternoon light gather energy and hold it into evening. Metal surfaces warm rapidly. Rooftops continue radiating heat after sunset. These are not small local details. Spread across an urban area, they alter the entire lower atmosphere over the city. The shape of the built environment matters as much as the material. Streets bordered by tall buildings form canyons of stone, glass, and concrete. Sunlight enters these spaces, reflects between surfaces, and becomes trapped in ways that prolong warming. Airflow is often weakened or made irregular by the same structures. Wind may pass freely above rooftops while street level remains comparatively stagnant. Heat released by traffic, cooling systems, industrial activity, and dense human use adds another layer, though in many heat waves the dominant source remains the stored solar energy of the urban fabric itself. The city does not merely sit under the hot air mass, it modifies it from below and within, turning regional heat into an even more persistent urban burden. During the day, the difference between city and countryside may vary depending on cloud cover, wind, vegetation, and the character of nearby rural land. In some dry open regions, bare soil can also become extremely hot under strong sunshine. But at night the urban effect often becomes clearer. Rural surfaces, especially where vegetation and soil moisture remain, can cool more efficiently after sunset. This city cools more slowly. Heat that has entered roads, walls, and roofs through many hours of direct sunlight now returns to the surrounding air. Long-wave radiation leaves the surfaces, but some of it is intercepted and reabsorbed within the urban geometry. The narrow view of the sky from street level can reduce radiative loss compared with open countryside. The result is a slow release rather than a rapid reset. Night remains warmer, dawn begins from a higher starting point, and the next day's heating starts early from that elevated base. This nocturnal warmth is one of the most dangerous urban features of an April heat wave. The body relies on cooler nights for recovery from daytime thermal stress. When indoor and outdoor temperatures remain high after dark, that recovery becomes incomplete. Bedrooms in poorly ventilated or poorly insulated housing retain the day's accumulated heat. Upper floors beneath roofs may stay especially warm. Small apartments surrounded by sun-heated walls may become reservoirs of nighttime discomfort. In wealthier districts, mechanical cooling can reduce some of this burden, though it also expels heat outdoors and can intensify the surrounding urban air. In less protected settings, the warm night becomes a continuation of the heat wave rather than a pause within it. This city, through its stored energy, lengthens the duration of exposure even when the sun has gone. Vegetation offers one of the main urban differences between cooler and hotter neighborhoods. Trees provide shade, reducing the amount of solar radiation that reaches walls, roads, and pedestrian surfaces. Plants also cool the air through transpiration when water is available. Where parks, gardens, and tree-lined streets are abundant, local temperatures can be lower than in densely paved districts. Where these features are scarce, the city's hard surfaces dominate. In many urban heat events, the sharpest thermal contrasts are found not between city and countryside alone, but within the city itself. One district may have shaded streets and irrigated green space. Another may be mostly asphalt, concrete, and exposed roofing. The April heat wave then acquires a social geography written into land cover, infrastructure, and planning. Water availability also matters in urban settings. Impermeable surfaces such as pavement and roofing reduce infiltration, which means rainwater often runs off quickly rather than soaking into the ground. This limits the amount of moisture stored locally for later evaporative cooling. Even after rain, the city may dry rapidly because thin soil layers and engineered drainage carry water away. In prolonged dry weather, this leaves the urban surface with few natural cooling pathways. More of the sun's energy is therefore spent directly on raising temperature. The same principle that affects dry rural soil appears here in a built form. A dry sealed surface heats quickly and sheds that heat slowly. April introduces an important timing problem in cities. Because the season is still early, many buildings and daily routines may not yet be adapted to persistent heat. Cooling systems may not be fully in use. Public cooling spaces may not be widely prepared, and people may still occupy homes and workplaces designed for milder spring conditions. The urban heat island can therefore turn an unusually early heat spell into a more severe health challenge. Surfaces already behave like midsummer under strong sunlight, but social systems may still be operating under spring expectations. This mismatch between season and exposure is part of why early heat is often dangerous even before the very hottest months arrive. Observations from many regions show that urban areas are commonly warmer than surrounding rural zones, especially at night, and that this difference can worsen during clear, calm weather. These are exactly the conditions favoured by blocking highs and April heat events. Climate change adds another layer by increasing the background temperature onto which the urban effect is superimposed. A city that once retained warmth after a hot spring day now begins that day from a warmer baseline than before. It remains uncertain in specific locations how changes in urban design, vegetation, reflective materials, or local wind patterns may alter future heat island intensity. But the general relationship is well established. When regional heat and urban heat retention occur together, nighttime risk rises sharply. At street level, the city's contribution to the heatwave is often experienced through surfaces rather than air alone. Pavement radiates warmth upward into the legs. Bus stops and station platforms hold heat. Buildings warmed all afternoon continue releasing energy long into the evening. Air in narrow alleys feels still and stale. Courtyards surrounded by walls cool only slowly. Heat seems to come from every direction because it does. The air is warm, but so are the surfaces enclosing it. In this environment, shade, airflow, and nighttime cooling become not small comforts but major determinants of safety. In this region of the story, the April heatwave enters the built landscape and changes character. Regional warmth arrives over the city, but the city stores it, deepens it, and releases it after dark. Dark surfaces absorb sunlight, dense materials hold heat, streets restrict ventilation, and limited vegetation reduces natural cooling. Nights remain warm because the urban fabric continues to return the day's energy to the air. The climate signal therefore becomes sharper inside the city, where spring heat is not only endured but retained. What was a regional atmospheric event over land becomes, in the urban environment, a sustained burden of radiant surfaces, slow cooling, and persistent nocturnal warmth. Beyond the dense surfaces of the city, the wider land cover begins to separate into different thermal characters, and the heat wave reveals how strongly those characters matter. Fields, forests, grasslands, orchards, scrub, wetlands, and bare ground do not respond to April sunlight in the same way. Each surface receives radiant energy from above, but what happens next depends on colour, moisture, texture, canopy structure, and the depth of living cover. In this region of the story, the heat wave is shaped by the living and non-living skin of the land. Some surfaces shade themselves, hold moisture, and cool the air through evaporation. Others expose the soil directly, warm rapidly under clear skies, and return heat to the atmosphere with little restraint. The event that began as a planetary and atmospheric pattern now becomes legible in the details of leaves, stems, roots, and exposed earth. Forests often moderate daytime heating because their canopies intercept sunlight before it reaches the ground. Leaves and branches create layered shade, and the forest floor beneath them usually remains cooler than open land under the same sky. Trees also move water from soil to air through transpiration, which cools both leaf surfaces and the surrounding atmosphere when water is available. The rough structure of a forest canopy changes wind flow as well, producing turbulence that can mix air in complex ways. In April, especially in temperate regions, the exact effect depends on the stage of seasonal leaf growth. Evergreen forests already hold their canopy, while deciduous woodlands may still be emerging into full leaf. Even partial leaf cover can soften the heating of the surface below. But where spring growth is delayed, the protective effect may be incomplete. The heat wave then meets a landscape in transition, with some areas already shaded and others still open enough for strong sunlight to reach the ground. Grasslands and agricultural fields behave differently. A healthy, moist field with active growth can cool the air through transpiration, and may remain notably less hot than a nearby paved area or dry exposed plot. Yet a harvested field, a field with sparse cover, or a pasture under moisture stress can warm quickly. The openness of such land allows sunlight to reach the soil directly, and if that soil is drying, evaporative cooling weakens. In April, this can produce a large contrast even within a single rural district. One field may be green and moderately cooled by plant activity. Another, recently ploughed or lightly vegetated, may send strong sensible heat into the boundary layer through the afternoon. The lower atmosphere above a patchwork of land covers thus acquires a mosaic of temperatures, humidity levels, and turbulence, each linked to what lies beneath. Bare earth is among the clearest amplifiers of heat. Without shade from vegetation and without substantial surface moisture, it absorbs sunlight directly and warms rapidly. Its exact response depends on soil type, color, and composition. But the principle is simple. A surface with little water and little cover offers few defenses against solar heating. Construction sites, overgrazed ground, eroded slopes, recently cleared land, and drought-affected open terrain often become local centres of intense afternoon warmth. Their influence may extend beyond their own boundaries because heated air rises and mixes outward, contributing to the broader warming of the lower atmosphere. In a prolonged April heat wave, the repetition of bright days strengthens this contrast. Covered land retains some thermal balance. Bare land increasingly behaves like an exposed heat source. Wetlands and irrigated areas provide another important counterpoint. Where water remains near the surface, a greater share of solar energy is used for evaporation. This tends to lower daytime surface temperature and can create cooler local air, though it may also increase humidity. In some agricultural regions, irrigation can temporarily buffer crops and reduce peak land surface heating. Yet this cooling is conditional. It depends on water supply, infrastructure, and the willingness or ability to use that water during the event. It also remains local. A single irrigated district cannot offset a regional heatwave if surrounding landscapes are dry and atmospheric conditions remain stagnant. Wetlands likewise moderate heat within their reach. But if they shrink seasonally or suffer from water loss, that cooling influence contracts. April heat therefore reveals not just where water exists, but where it remains accessible enough to shape the thermal response of the land. The structure of vegetation matters as much as its presence. Tall trees create deep shade and a multi-layered canopy. Shrubs provide partial cover and can reduce direct ground heating, though usually less than forest. Short grasses may cool effectively when green and moist, but much less so when dry or sparse. Crops differ in height, leaf area, rooting depth, and timing of spring growth. A vineyard, an orchard, and a field of grain may all experience the same air mass yet produce different near-surface temperatures because their interaction with sunlight, soil moisture, and airflow differs. This is why the heat wave cannot be understood fully through air temperature alone. The surface beneath that air determines how strongly heat is generated, stored, and returned to the atmosphere hour by hour. Albedo, which is the fraction of sunlight reflected by a surface, also contributes to these differences. Pale dry grass may reflect more sunlight than dark moist soil. Dense forest canopies may absorb much of the incoming light, but then use part of that energy in transpiration rather than simply raising temperature. Recently burned or darkened ground may absorb more and heat faster. Texture changes matters too. Rough vegetation breaks up airflow and alters turbulence. Smooth bare ground behaves differently, sometimes allowing stronger near-surface heating with less shading and less retained moisture. Across a landscape of mixed covers, these physical differences generate small but meaningful local climates, each adding to the total shape of the event. In April, timing again becomes crucial. Many landscapes are still in seasonal transition. Crops may be newly planted, grasses may be uneven in growth, Forest leaf-out may vary with elevation and latitude. Some areas may still retain spring moisture, while others have already dried under clear skies. Because of this, an early heat wave can expose surfaces before they have reached their most protective state. A deciduous grove not yet fully leafed cannot shade like it will later in the season. A field not yet fully rooted cannot transpire like it will in early summer. The event then finds the land partially prepared and partially exposed, increasing its sensitivity. This is one reason April heat can feel surprisingly severe over landscapes that, a few weeks later, might resist warming more effectively. Human land use can intensify these contrasts, clearing forests, reducing tree cover, draining wetlands, compacting soils, or leaving large areas of ground exposed all tend to increase local heating potential. By contrast, agroforestry, shelter belts, soil conservation, and managed green cover can moderate temperatures to some degree. These choices do not control the regional air mass or the blocking high overhead, but they influence how the land receives and returns heat. Under a strong April event, their effects may be modest compared with the scale of the atmosphere, yet they remain meaningful where people work, where crops grow, and where ecosystems endure stress. Observations across many regions show that vegetated and well-watered surfaces are generally cooler during hot conditions than dry bare surfaces, while forests often maintain lower daytime land surface temperatures than open exposed ground. It remains uncertain how each local landscape will change under future warming, because rainfall, land management, fire, and seasonal plant cycles vary widely. Even so, the physical relationships are clear. Shade reduces direct heating. Moisture supports evaporative cooling. Living cover changes wind, light, and surface temperature. When those protections are reduced, heat intensifies more easily. In this region of the story, the April heat wave becomes a map of cover and exposure. Forests soften sunlight and cool through water movement. Green fields offer some resistance when moisture remains. Wetlands and irrigated ground buffer heat locally. Bare earth, sparse vegetation, and disturbed land warm quickly and send that warmth back into the air. The climate signal therefore deepens not only across cities and dry soils, but across the full diversity of the rural landscape. Heat is shaped by what covers the ground, by how alive and moist that cover remains, and by how much of the sun's April energy is turned into shade and vapor rather than temperature. Where cover fails, the heat wave finds an easier path. Within these varied landscapes of trees, fields, bare ground, and built surfaces, the heat wave finally settles into the immediate environments where people pass their days and nights. This is the region of streets, courtyards, factory floors, classrooms, bus stops, farm paths, tin roofs, concrete stairwells, small shops, and sleeping rooms. The atmosphere above remains important, and the land cover beneath still shapes the exchange of energy. But now the concern narrows to the thin zone where human life actually unfolds. In April, this zone can be especially vulnerable because the season still carries an expectation of moderation. Daily routines, housing practices, work schedules, and public systems may not yet be adjusted to persistent high heat. The result is a dangerous mismatch between the physical environment and human readiness. The warmth is no longer only something measured at a weather station. It is something held in walls, trapped in transit spaces, intensified on work surfaces, and carried indoors after sunset. The immediate human environment is shaped first by exposure. A person standing under direct afternoon sunlight receives not only the surrounding air temperature, but also radiant heat from the sun and from nearby surfaces, a paved street, a pale wall, a sheet metal roof, or a parked vehicle can all reflect or emit additional warmth. In shaded conditions, the same air temperature may feel more tolerable because the body is no longer absorbing so much external radiation. This is why two locations only a short distance apart can produce very different thermal stress. One may have trees, awnings, airflow, and shaded ground. Another may be open to full sun, surrounded by concrete and bordered by walls that store and release heat. The heat wave is thus experienced not as a uniform blanket, but as a pattern of micro-environments, each one shaped by material, shade, enclosure, and ventilation. Housing is one of the most important parts of this region. Homes do not simply shelter people from outdoor weather, they interact with it. A building with thick walls, reflective roofing, shaded windows, and good airflow can reduce indoor heat gain during the day and release stored warmth more slowly and safely at night. A structure made of heat-absorbing material with poor insulation, low ceiling height, limited cross-ventilation, and direct solar exposure may do the opposite. In April, this can be particularly harmful because many homes are still being used as if nights will cool naturally. Windows may be opened at the wrong times, curtains may not yet be drawn against strong daytime sunlight, and cooling equipment may not be available, affordable, or fully prepared. The dwelling then becomes an extension of the outdoor heat event, storing energy by day and delaying recovery after sunset. Roofing plays a large role in this. Dark roofs absorb substantial sunlight. Metal roofs can heat rapidly and transfer warmth downward into upper rooms. Flat concrete roofs may hold heat into the evening and release it after the sun has set. In dense, low-income settlements or compact apartment districts, these effects are multiplied by crowding and limited air movement between structures. Narrow lanes trap warmth. Shared walls reduce opportunities for cross breezes. Upper floors may remain hotter than lower ones because of rising indoor air and direct roof heating. In such places, the April heat wave is not only an outdoor event, it becomes a condition of prolonged indoor thermal load, especially during the evening and night. Work environments add another layer of exposure. Outdoor labour in agriculture, construction, transport, street vending, sanitation, and delivery places people directly under the seasonal sun at the hours when surface and air temperatures peak. Indoor work can also be hazardous when ventilation is poor or machinery adds heat to the space. Workshops with metal roofing, kitchens, warehouses, market halls, and transit depots may become much hotter than the surrounding outdoor shade temperature suggests. In April, early season heat can catch these settings at a moment when schedules have not yet shifted, and protective practices may not be routine. Midday rest periods may not be fully adopted. Water access may be insufficient. Clothing and expectations may still reflect the habits of a milder season. The environmental heat is therefore joined by social timing, and the two combine to increase risk. Public space determines much of the burden for people who do not control their surroundings. A shaded park, a tree-lined pavement, a well-ventilated bus shelter, or an accessible cooled community building can make a large difference during a heat event. The absence of these features leaves the body exposed to continuous radiant and convective load. Waiting for transport in a paved interchange, standing in line outside a clinic, walking along an unshaded road, or living in a neighborhood without trees can turn ordinary tasks into prolonged heat exposure. In cities and towns, the distribution of such spaces is often uneven. Some districts possess abundant shade and cooling options. Others consist largely of exposed concrete, limited greenery, and buildings that retain warmth. The heat wave is therefore filtered through inequality in infrastructure as much as through weather. Nighttime conditions in human surroundings are often the clearest test of danger. When indoor spaces fail to cool, the body cannot recover fully from the previous day. Bedrooms that remain warm into the early morning, especially in crowded housing, increase cumulative stress. Air movement is crucial here. A modest nighttime breeze can improve comfort substantially if windows and openings allow it to pass, but in dense neighborhoods, enclosed courtyards, and top-floor rooms under heat-storing roofs, ventilation may be too weak. Fans, where available, can help by increasing air movement over the skin, though their benefit depends on temperature, humidity, and access to electricity. Air conditioning reduces risk in many settings, but it is unevenly available and can be vulnerable to power failure during periods of high demand. For many people, the most important factor remains whether the surrounding built environment permits the night to cool naturally. In a mature April heat event, it often does not. Travel corridors create their own thermal environments. Vehicles parked in the sun become enclosed heat traps within minutes. Trains, buses, and minibuses with inadequate cooling or ventilation accumulate warmth through windows, crowding, and engine or brake systems. Asphalt roads radiate heat upward. Footbridges, platforms, and stations made of metal and concrete hold solar energy and limit shade. The heat wave then accompanies daily movement, not just stationary life. Commuting, walking to school, crossing an open market square, or cycling along exposed routes all become part of the total exposure profile. In early season events, the danger is heightened because people may not yet have adjusted departure times, hydration habits, or route choices in response to strong heat. Schools, clinics, and care facilities illustrate how this environmental layer reaches into institutions. A classroom with many occupants, little airflow, and direct western sunlight can become a zone of significant heat stress by afternoon. A clinic waiting room may be crowded, enclosed, and difficult to cool. Older adults, infants, and people with chronic illness often spend more time indoors, but indoors does not always mean safer. The quality of the immediate environment matters more than the simple distinction between outside and inside. Shade, ventilation, materials, crowding, and nighttime cooling all determine whether a place buffers heat or accumulates it. Observations from many regions show that heat risk rises sharply where housing quality is poor. Nighttime cooling is limited, access to shade and water is restricted, and people must remain active during the hottest hours. These are not secondary details. They are central mechanisms through which a regional heatwave becomes a public health event. It remains uncertain how each specific community will adapt in the future, because design, investment, local climate, and social support vary widely. But the physical principles are clear. Surfaces store heat, enclosed spaces trap it, shade reduces radiant load, airflow improves cooling. Safe environments depend on these basic elements. In this region of the story, the April heatwave enters daily life completely. It moves from fields and forests into homes, work sites, transit spaces, and sleeping rooms. It is shaped by roofs, walls, windows, trees, shade structures, crowding, ventilation, and the ability of people to change their routine. The climate signal is no longer abstract. It is present in the warm stairwell at dusk, the unshaded walk at noon, the metal roof over an upper room, the stalled bus, the airless classroom, and the bedroom that remains too warm for rest. Here the warning is carried not just by temperature, but by the environments through which human life must continue. while the heat settles deeper into the season. Inside these heated surroundings, the final boundary between environment and harm is the human body itself. The body does not passively receive heat. It works constantly to maintain a stable internal temperature despite changing conditions outside. This regulation depends on circulation, sweating, breathing, behavior, and the transfer of heat between skin and air. In ordinary spring warmth, these systems usually operate with ease during an April heat wave, especially one that arrives early and persists over many days. The same systems may be pushed toward their limits. At this inward level, the climate signal is no longer only a matter of hot surfaces, stagnant air, or clear skies. It becomes a question of physiology, of whether the body can shed heat as fast as the environment and its own metabolism add it. Human beings produce internal heat all the time. Muscles generate it during movement. Organs generate it through metabolism, which is the chemical process by which the body uses energy to sustain life. Even at rest, the body must release this internal heat to remain stable. It does so through several pathways. Heat can move directly from skin to cooler surrounding air by convection, if the air is cooler than the skin and moving enough to carry warmth away. It can also leave through radiation if the surrounding surfaces are cooler than the body. A smaller amount is lost through conduction when skin contacts a cooler object. The most powerful cooling mechanism in hot weather, however, is evaporation of sweat. When sweat changes from liquid to vapor on the skin, it removes heat. This is why the body can tolerate high air temperatures more effectively when the air is dry and moving. During an April heat wave, these pathways begin to narrow. If the surrounding air becomes warm enough, convection becomes less effective because the temperature difference between skin and air shrinks. If nearby walls, pavement, roofs, and ground surfaces are also hot, radiant cooling weakens and may even reverse, meaning the body absorbs radiant heat instead of losing it. If humidity is high, sweat does not evaporate as readily, because the air is already holding much water vapor. In that case, the body may continue producing sweat, but the cooling benefit declines. Clothing, limited airflow, direct sunlight, and physical exertion make the problem worse. What begins outside as a weather event now becomes an imbalance within the body between heat gain and heat loss. The first stage of response is usually an increase in blood flow to the skin. Blood vessels near the surface widen so that internal heat can be brought outward and released more easily. Sweating increases as well, and together these responses can be very effective if the environment allows them to work. Yet they come at a cost. Sweating removes water and salts. Greater skin blood flow places additional demand on the heart because circulation must support both internal organs and cooling at the same time. In a prolonged heat event, especially one with warm nights, these demands accumulate. Dehydration can develop gradually if water intake does not keep pace with losses. Blood volume falls. The heart must work harder. The ability to sweat may diminish as dehydration worsens. The body then enters a more fragile state in which temperature can rise faster. Humidity is one of the most important modifiers of this stress. In dry air, sweat can evaporate quickly, often allowing the body to remain stable even in high temperatures if shade, rest, and water are available. In humid air, evaporation slows. Sweat may remain on the skin or drip away without removing enough heat. The body can feel overwhelmed even at lower air temperatures than in a dry climate because its main cooling method is being blocked. This is why humid April heat along some coasts or in tropical and subtropical regions can be especially dangerous. The heat may not look extreme by temperature alone. Yet the physiological burden can be severe because nighttime recovery is poor and daytime sweat cooling is impaired. Exertion changes the picture quickly. Walking, lifting, climbing, carrying, farming, construction work, and even routine commuting all generate additional metabolic heat inside the body. Under cool or moderate conditions, this extra heat is manageable. Under hot conditions, it adds to the already difficult task of maintaining balance. A person working in direct sun on a still April afternoon may be dealing with solar radiation from above, radiant heat from the ground and surrounding surfaces, warm air that does not cool effectively, and internal heat from muscle activity. The body responds by driving circulation and sweating harder. But those systems have limits. Once heat gain outpaces heat loss, core temperature rises. This is the beginning of heat strain, the physiological stress caused by the body's effort to cope with environmental heat. The signs of growing heat strain can begin subtly. Fatigue increases, thirst becomes strong, the skin may be wet with sweat or, in some cases, become unexpectedly dry if regulation is failing. Dizziness, headache, nausea, muscle cramps, and weakness may follow. Attention and judgment decline. Coordination worsens. These effects are not only discomfort, they are signals that the body's balancing systems are under pressure. If cooling, rest, and hydration do not occur, the condition can progress to heat exhaustion, in which circulation and fluid balance are seriously stressed. Beyond that lies heat stroke, a medical emergency in which the body can no longer control internal temperature adequately, and core temperature rises to dangerous levels. This can damage the brain, heart, kidneys, and other organs and can become fatal without urgent treatment. Warm nights are especially harmful because they deny the body a period of restoration. After a hot day, the body benefits when ambient temperature falls enough for skin blood flow and sweating demand to ease. Sleep also matters, because rest supports recovery of fluid balance, cardiovascular stability, and general resilience. In an April heat wave with elevated nighttime temperatures, that recovery is incomplete. The next day begins before the previous day's strain has fully ended. Over several days, this cumulative burden can become severe, especially for older adults, infants, pregnant people, outdoor workers, and those with heart disease, lung disease, kidney problems, or limited access to water and cooling. Medications can also change risk by affecting sweating, hydration, or circulation. Acclimatization is another key physiological factor. Acclimatization is the process by which the body gradually adapts to repeated heat exposure over days or weeks. It can improve sweating efficiency, reduce salt loss, and lessen cardiovascular strain during later heat exposure. April heat waves are often dangerous precisely because they arrive before full acclimatization has occurred. People who might cope better in midsummer may struggle more during an early season event because their bodies have not yet adjusted. This is one reason early heat can produce outsized health impacts even when later summer temperatures may eventually exceed it. The timing interacts with physiology. The event reaches inward before adaptation is complete. Observations across many regions show that periods of unusual early heat are linked with increases in illness and death, particularly where nights remain warm and where humidity, poor housing, or strenuous activity intensify exposure. Scientists also find that warming climates increase the likelihood of conditions that challenge the body's cooling systems, including more frequent hot days and warmer nights. It remains uncertain how adaptation, public health measures, and changing behavior will alter future vulnerability in every place. But the biological principles are settled. The human body must release heat to survive. When the environment prevents that release, risk rises quickly. In this region of the story, the April heatwave reaches its deepest practical meaning. The sky, soil, city, and air mass all matter because they shape the conditions under which the body must keep itself cool. Warm air reduces convective relief. Hot surfaces reduce radiative cooling. Humidity weakens sweat evaporation. Exertion adds internal heat. Dehydration strains circulation. Warm nights deny recovery. The climate signal is therefore written into pulse rate, sweat, fatigue, thirst, and rising core temperature. It is here, within the body's steady effort to maintain balance, that a season of unusual heat becomes a direct test of human limits. After the body has been reached by heat, the inward path turns once more, not into flesh or shelter, but into evidence. This is the region where scientists study what has happened, compare it with the past, and ask whether an April heat wave is only a passing expression of ordinary variability or part of a broader and deepening pattern. The atmosphere, land, city, and human body all provide the physical reality of the event. Records and attribution provide its measured meaning. In this part of the story, heat is translated into observations, anomalies, distributions, and long-term trends. The concern is no longer how the event feels on the skin or how it builds in soil and air, but how it appears in data gathered across years, decades, and regions, and how scientists determine whether the changing climate is altering the odds of such events. The first step is observation. Meteorological records come from weather stations, satellites, ocean measurements, reanalysis products, and other monitoring systems that together describe temperature across the globe with increasing detail. Surface stations provide long time series in many regions, allowing scientists to compare a particular April day or sequence of days with the local history of that same calendar period. This matters because heat is seasonal. A temperature that is ordinary in midsummer may be extraordinary in April. Scientists therefore often examine anomalies, which are departures from a local average for a given place and time of year. An April heat wave may stand out not only because it reaches a high number, but because it rises far above what that region usually experiences so early in the warm season. These records also allow scientists to examine extremes rather than averages alone. Average warming is important, but a heat wave is an extreme event, and extremes respond to climate change in ways that are often more consequential for human life. Researchers look at the hottest daytime temperatures, the warmest nights, the duration of consecutive hot days, the timing of first seasonal heat events, and the spatial extent of unusual warmth in many regions. Observations indicate that hot extremes have become more frequent and more intense as the climate has warmed. Warm nights have also increased in many places, which is especially important because nighttime recovery is central to health and ecosystem resilience. The record therefore shows not only a warmer average climate, but a shifting distribution of temperature in which the upper tail, the hottest part of the range, increasingly expands. An early season event like an April heatwave carries special statistical significance because timing itself becomes part of the signal. Scientists can examine whether the first occurrence of very warm conditions in a year is arriving earlier than it once did, whether thresholds associated with heat advisories are being crossed sooner, and whether the pace of spring warming has changed in certain regions. This does not produce a uniform answer everywhere. Climate change interacts with local geography, circulation, soil moisture, snow cover, and ocean influence. Some places show stronger trends in early heat than others, yet across broad areas, observations indicate that warming has increased the likelihood of unusually hot spring conditions. including events that appear earlier in the season than older records would suggest. To interpret these trends correctly, scientists must separate weather variability from climate signal. Weather variability includes the natural shifts that occur from year to year because of circulation patterns, ocean conditions, volcanic influences, and other internal fluctuations in the climate system. A single heat wave can still occur without long-term climate change, just as a cold spell can still occur in a warming world. The key scientific question is not whether climate change creates each event from nothing, but whether it changes the background conditions and the probability of such events. Attribution science addresses this by comparing the observed climate with a modelled climate in which human-driven greenhouse gas increases are absent or reduced. Researchers then estimate how the odds or intensity of an event differ between those worlds. This work does not claim impossible precision. It does not say that one fraction of a degree belongs purely to weather and another purely to climate with absolute certainty. Instead, it uses many simulations, observational constraints, and statistical methods to estimate how human influence has altered risk. In the case of heat, the signal is often clearer than for some other extremes because temperature responds directly to the warming effect of greenhouse gases. When the baseline climate warms, heat thresholds become easier to exceed. A blocking pattern that once produced a strong April warm spell may now produce a more severe event because it is operating atop a warmer land surface, warmer air mass origins, and warmer nights. Attribution studies of many recent heat events find that human-caused warming has increased their likelihood and, in many cases, their intensity. It remains uncertain for any one event exactly how all local factors combine, especially where observations are sparse or regional dynamics are complex. But the general relationship between greenhouse warming and heightened heat risk is one of the strongest findings in climate science. Scientists also examine mechanisms in the records. Soil moisture data can show whether land drying contributed to amplification. Snow cover data can reveal whether earlier melt exposed darker surfaces sooner. Sea surface temperatures may indicate whether ocean warmth influenced circulation or coastal humidity. Upper air records can show persistent ridges and subsiding air. In this way, attribution is not only statistical, it is physical. Researchers ask whether the event occurred under conditions consistent with known heat-amplifying processes, and whether those processes themselves are being altered by a warming climate. Sometimes the answer is direct. Sometimes it remains partial. The science grows strongest where observations, models, and physical reasoning agree. Long-term records also reveal another important feature. As the climate warms, what was once rare can become more common, and what was once remarkable can become part of a new normal. This does not mean society experiences such events as ordinary. Their impacts may still be severe, but statistically thresholds shift. Return periods shorten. A temperature that might once have occurred only infrequently in April may now appear much more often. This is one reason scientists are careful about language such as record-breaking. Records are important, yet they are part of a larger changing distribution. Each new record sits within a trend that may already have lifted the whole range upward over time. The limits of certainty remain important. Climate models vary in regional detail. Historical observations are denser in some places than others. Urbanization can affect local station records if not accounted for carefully. Natural variability in circulation can still dominate the pattern of a single season in one region. These uncertainties do not erase the larger picture. They define its edges. Scientists can say with high confidence that the planet has warmed. The heat extremes have increased across many regions, and that human influence has made many such extremes more likely. They may be less certain about how much a specific circulation feature changed because of warming, or how one local April event would have unfolded under a different historical background. Good science preserves both kinds of statements at once. It identifies the robust signal and names the remaining limits. In this region of the story, the heatwave becomes legible as evidence. Thermometers, satellites, models, and long records show that the climate baseline has risen and that hot extremes increasingly emerge from that raised floor. The unusual warmth of April is examined not only as a moment of weather, but as part of a shifting pattern of probability, seasonality, and impact. Scientists do not read one hot week in isolation. They place it within decades of observation, compare it with worlds simulated with and without human influence, and test whether the physical mechanisms align with the statistical findings. The warning therefore deepens into knowledge. What the body endures and the city retains, the record confirms. The event is measured against history, and in that comparison the broader climate signal begins to stand plainly within the heat. At the deepest level of this subject, the April heat wave is no longer only an event in air, land, city, or body, and no longer only a pattern verified by records and models. It becomes a warning carried by timing itself. Heat in the hottest part of the year is dangerous, but heat that arrives far earlier than the season once prepared people, ecosystems, and infrastructure to expect carries a different significance. It reveals that the climate signal is not limited to a gradual rise in average temperature. It also appears in the changing calendar of exposure, in the way warmth reaches into spring with greater force, and in the way the margins between seasons become less reliable than they once seemed. An April heatwave matters because it shows that dangerous heat is no longer confined as clearly to the traditional bounds of summer. The warning lies in this widening of the season of risk. Early heat is powerful because so many systems are calibrated by habit, biology, and design to the old rhythm of the year. Human bodies are not yet fully acclimatized. Buildings may still be operated with spring routines rather than summer protection. Power systems may face sudden cooling demand earlier than expected. Crops may be in sensitive phases of emergence or flowering. Trees may have only partial leaf cover. Rivers, soils, and reservoirs may still reflect the hydrological conditions of late winter and early spring rather than the more managed expectations of high summer. A heat wave in April therefore tests a landscape and a society before many of their normal seasonal defences have taken shape. This is why the event carries such strong meaning. It exposes vulnerability not only to temperature, but to changed timing. In climate science, timing is one of the clearest ways a warming world reveals itself in daily life. A shift of a few weeks in the arrival of dangerous heat may appear modest in abstract terms, yet its effects can be large. It lengthens the annual period during which health systems must prepare for heat illness. It expands the season during which outdoor labour must manage thermal risk. It alters the window in which crops and livestock face stress. It may increase evaporation earlier in the year, drying soils sooner and preconditioning the land for later summer heat. The warning within April is therefore cumulative. It is not merely that one month becomes hotter. It is that an earlier start can reshape everything that follows, pushing stress forward in time and giving subsequent warm months a drier, more fragile beginning. This deeper signal is visible in the contrast between weather and climate. Weather explains why a particular block forms, why skies remain clear, why winds weaken, or why one region heats more than another in a given week. Climate explains why those familiar weather ingredients now tend to produce higher temperatures when they do occur. In the case of April heat, The climate signal becomes especially clear because the event presses against expectations built over long experience. A blocking pattern in midsummer may still be interpreted by many as severe but seasonally imaginable. The same persistence in April can feel startling because the atmosphere is now delivering summer-like danger before the cultural and environmental markers of summer have fully appeared. That mismatch is part of the evidence. The season itself no longer behaves within the older range of intuitive boundaries. Scientists are careful here, because not every warm April day is a climate warning by itself. Natural variability remains real. Some years will bring unusually hot spells through ordinary atmospheric fluctuation, and local conditions will continue to differ. It remains uncertain for any single event exactly how much of its specific timing or local severity arises from circulation, soil moisture, ocean conditions, or the warmer global baseline. Regional trends are not identical, and early season heat does not increase at the same rate everywhere. Yet the broader understanding is firm. As greenhouse gases continue to warm the planet, the probability of hot extremes rises, and the parts of the calendar vulnerable to such extremes can expand. What was once a rare early intrusion of dangerous heat becomes more plausible and, in many places, more frequent. The meaning of this is practical as much as scientific. A warning is useful only if it changes attention. April heat calls attention to thresholds that are no longer protected by the old spacing of the seasons. Public health plans built around later summer peaks may need to activate sooner. Urban design that once treated spring as a moderate interval may need to account for stronger early radiant load and warm nights. Agriculture may need to navigate a longer hot season beginning from earlier moisture loss. Schools, workplaces, and transport systems may need to respond before traditional summer schedules begin. These are not speculative transformations of distant decades only. In many regions, they're already emerging as sensible responses to observed patterns of earlier warmth and more frequent extremes. The natural world also receives this warning in layered ways. Pollinators, flowering cycles, bird migration, stream temperatures, and soil microbial activity are all tied to seasonal timing. Heat arriving too early can disrupt these patterns, especially when paired with dryness. Young plants may face thermal and moisture stress before roots deepen. Snow-fed systems may see faster melt and earlier runoff loss. Forests not yet fully leafed may provide less local cooling. Even where no immediate ecological collapse occurs, the event reveals that long-evolved seasonal coordination is being asked to function under altered timing. The signal is therefore broader than human discomfort or record temperatures. It touches the organization of spring itself. There is also a deeper emotional and cultural meaning, though it remains grounded in physical reality. Seasons help societies arrange labor, school terms, clothing, architecture, food systems, and expectations of daily life. When dangerous heat begins to arrive outside the period once associated with it, that shared calendar of anticipation weakens. This is not merely a feeling of surprise, it is a measurable shift in risk. The climate signal becomes harder to ignore because it intrudes into months that still carry the name and memory of gentler conditions. April heat does not simply add one more hot day to the record. It alters the edge of the warm season, and by altering that edge, it changes how much of the year belongs to heat. In the deepest scientific sense, the warning within April is a warning about baseline. A warmer baseline means that ordinary atmospheric patterns are increasingly sufficient to generate extraordinary outcomes. Clear skies, weak winds, dry soils, and high pressure are not new. What is new is the thermal world in which they now operate. The atmosphere begins warmer, the land dries faster, nights remain warmer, Cities release more stored heat into already heated air. Bodies face stress sooner in the year. Records show these shifts accumulating. Attribution studies show the odds changing. The warning, therefore, does not depend on any single dramatic theory. It emerges from many ordinary processes becoming more dangerous together on a warmer planet. This final region gathers the full inward path into one meaning. From sunlight over a tilted Earth to moving circulation belts, from upper air ridges to blocked skies, from settled air masses to weak winds, from clear days to inland amplification, from drying soils to heated cities, from patchy land cover to human surroundings, from the body's cooling struggle to the record of changing extremes, each layer has carried the same message inward. April heat is not only a hot spell. It is a sign that the climate system is loading heat earlier into the year, extending exposure into seasons once more buffered from it, and reducing the reliability of old seasonal limits. The precise regional details will vary. Some mechanisms will remain uncertain in individual events, but the central signal is clear enough to stand without exaggeration. Dangerous heat is arriving in places and times that show the background climate has shifted. The warning, then, is not contained in one thermometer reading. It lies in the convergence of evidence. It lies in the earlier timing, the warmer nights, the dry ground, the stressed body, the altered probability, and the widened season of exposure. April becomes significant because it reveals climate change not as an abstract future state, but as a present rearrangement of when heat arrives and how fully it can take hold. The deeper message is plain and steady. A month once associated in many regions with transition is increasingly capable of carrying the burden of extremes. That is the climate signal that cannot be ignored. It is the quiet movement of danger inward through the calendar itself, until spring no longer guarantees the margin of safety it once seemed to hold. The heat settles now into a quieter view. The planet remains under the same April sun, turning with its usual steadiness, and the atmosphere continues its old work of moving warmth, moisture, and air from one place to another. Yet the meaning of the season has shifted. What once arrives later can now arrive sooner. What once feels unusual can begin to repeat. The signs do not need drama. They appear in clear skies held too long, in soil that dries too quickly, in cities that do not cool after dark, in bodies that struggle before summer has fully begun. Observations indicate that the warming background of the climate is changing the conditions in which ordinary weather unfolds. A high-pressure system, a dry week, a stretch of bright days, and a settled air mass are familiar parts of the atmosphere. What changes is the heat they now produce. It remains uncertain how every region will respond in detail, because oceans, clouds, circulation, land cover, and local geography all shape the outcome differently. But the broader pattern is steady enough to be seen across records, across landscapes, and across the calendar. April no longer stands only as a threshold to warmer months. In many places it is becoming part of the season of heat itself. That is why an April heatwave carries more than immediate discomfort. It reveals the quiet extension of risk into earlier days of the year, when habits, homes, ecosystems, and expectations are less prepared. The warning is not separate from the season. It is woven into it. The earth continues to tilt, oceans continue to moderate, winds continue to shift, and clouds continue to gather or fail to gather. Within these ordinary motions, the climate signal grows clearer. Heat arrives earlier, lingers longer, and settles more deeply into land and life. The month remains April, but the conditions within it are changing, and that change speaks in a calm, persistent language that is difficult to dismiss.